Welcome everyone. In today's class, we will try to introduce the scheduling problem. So, we have already seen that high level synthesis is a process of converting an high level behavior written in C or C++ into an equivalent design in RTL level, right. And we have also seen that this high level synthesis is actually consists of several sub steps, and the sub steps are basically pre-processing, scheduling, allocation, binding, data path controller, generation, and then finally we will get the RTL, right. So, what we are going to do is today we are going to take this schedule steps, and then we try to formally define what is the problem here and what are the variations of the problem, and that we are going to discuss in today's class, right. So, we have already discussed that once we have given a behavior, it is basically it has a control flow and data flow graph will be extracted from the C code, and then it is basically you have set of basic blocks in your program, and there is a control flow among the basic blocks, right. So, for the loop there will be a package, for if else there will be a branch, and so on, right. And basic block is basically a sequence of operations whether there is no control branch, there is no control flow, right. It is a sequence of operations, and the way we planned the whole high level synthesis is that we will take one basic block at a time and try to schedule the operations there. We try to identify the resource required for that particular block, and then we will try to find out the interconnections and so on. And then what we can actually do is basically you try to find out the operations that are across basic block, you can also share the resource, right. But scheduling we can do independently of these blocks because they are non overlapping, right. So, what we can do, we can take a basic block at a time, we will schedule the operations there, and I can take one basic block at a time and schedule all those things. And during allocation and binding, when we are going to find out the number of FUs needed, number of register needed, what we can do is we can actually not only find out the resource required for one block, but also we can share resource across basic block also, right, because operations into basic block, if they are in series, we can share the registers even if they are in branch, right. So, although they are looks parallel, but they are in mutual exclusive branch, then also I can say use the same resource for both the branches, because in at a given time only one of the branch will execute, right. So, not both the branches will be executed. So, these are all detail we are going to discuss in the classes, but the bottom line here is try to say that we can take one basic block at a time, and then within the basic block the operations are there and we want to schedule them. In the example that working example that we have taken here is the DIFFQ example, and we have seen that for this example we have the control flow graph is this, and this basic block is basically the reading the inputs. This basic block is the loop body, right. This is the loop body where these are the operations are there, and this basic block is just writing the output, right. So, which will happen here, right. So, this is how we extract this, and the control flow is known, and within the basic block also we have discussed in previous classes that these operations are two big expressions, executing them in a single clock is something is not a good idea. So, better to break this operation into 3 address from or unit operations, and then you try to schedule that. Okay. So, let us try to go more into that this schedule steps. So, in C, if you have say have this operations with you, right. So, what I am going to do is here I am going to take these basic blocks, and then I am going to discuss the scheduling on the context of the operation given in this basic block. Okay. The similar thing can be done for other basic blocks of the program. Okay. So, now let us try to understand what is scheduling and what is the objective should be here, right. So, you have set of operations, there are 11 operations here, right. And if you give this into I mean if you run this program say only this basic block in using your processor, what is going to happen? It will execute these operations, then it will execute this and this and this, right. So, this is a top down manner, right. It will be executed in top down manner, right. So, what is the advantage of or disadvantage of this? Advantage is that because we are executing in the top down manner, the dependency is already is taken care of, right. So, for example, we have already discussed this this part that operation T1 is getting defined here the variable and it is getting used here. So, you cannot execute this operation before this operation, right. So, but if you execute them in a top down manner, automatically the dependencies, read after write dependencies or write after read dependencies are automatically taken care of. So, that is something is advantage. So, now in scheduling what we try to do, we have 11 operation, I want to schedule them. The obvious solution that you can think of, you use 11 clock to do this, right. So, in fast clock you do this V1 exactly in the top down manner, you execute it. In fast clock you do the operation V1 and then second clock operation V2 and so on. Obviously, this is a correct solution because this is how these things are going to happen in the processor, right. I am going to do this sequentially, but in hardware we try to improve the performance, right. So, the question that I am going to ask now myself, that is it 11 steps is necessary here? Can I have less step to execute this? The answer is yes, right. That the answer is yes, because yes, I can do by parallelizing such certain operations in the execution in the hardware, right. So, what does it mean? It means that once you execute the operations, it is not necessary that you execute them in one by one, rather you try to parallelize the execution of the operation, right. So, that means you try to execute more than one operations at a time. And so, obviously, what are the operation can be executed in parallel? The operations that has no dependencies. So, if there are two operations which is independent to each other, I can schedule them in parallel, and that is what is the scheduling objective, right. You try to find out the maximum parallelism within the behavior, because the behavior is a straight line of code. I mean, it is without further analysis, it is not possible for you to identify the parallelism, right. And for that we discussed in previous classes that you draw the data flow graph, right, data dependency graph. So, in the data dependency graph you identify the dependencies and you draw the graph. So, in the data dependency graph, each node represent one operations, right. So, this V1 is representing these operations and so on, right. And then if there is a dependency between two operations, just like this V1 and V5, you add an edge, right. So, that V1 to V5 there is an edge. So, wherever there is a dependency between two operations, you add an edge in this diagram and then this gives the dependencies. And once you try to parallelize or you try to schedule the operations, you try to schedule the operation such a way that it does not violate this dependency, right. So, for example, you cannot execute this V1 and V5 in the same time step ideally, right, because then there is a you cannot store this value T1 intermittently, right. So, there is a option of operation chaining I am going to discuss later, but in general if you want to execute one operation at a clock, this V1 and V5 should not run in parallel, because V5 depends on operation V1 and so on, right. So, in schedule now I will try to find out maximum parallel number of operations and I try to schedule them. So, if you take this behavior, I mean from the diagram that I have shown, I mean one possibility is that you execute this V1, V4, V5, V1, V2, V4 and V10 in timestamp 1, and then this V5, V3 and V9 in timestamp 2, and this in timestamp 3 and this is timestamp 4, right. So, we can understand that for this behavior, instead of 11 cycle, there is a solution which can take 4 cycle, right. So, I can understand that there is a huge improvement, right, from 11 cycle to execute this body, I can execute the things in 4 cycles, and that is what schedule does, right. So, given a basic block or series of program, it try to identify that operations, the number of time or the cycle you need to execute this behavior, and that is called latency. Okay. So, it try to identify the latency of the program, which is the number of timestamps. So, for this example my lambda or the latency is equal to 4. So, to execute this behavior by this schedule I need 4 cycle, right. So, the latency of this schedule is 4. Okay. And also the important thing is, it is not about that identifying only the number 4. You have to say this operation V1 is happening in timestamp 2, operation V6 is happening in timestamp 3 and so. That means that start time of the operations also is get determined. Okay. So, where this operation is getting executed, starting his execution. Okay. So, that something is also determined. So, schedule given a program or given sequence, a basic block or sequence of operations, it determines the total latency of the design, that means how many clock cycle I need to execute the behavior, and also the start time of each program, each operations within the basic block. Okay. So, that is what is scheduling, right. So, that is the overall thing, but there are maybe very many variations of scheduling. It is not that it is so straightforward you do it always in 4 cycle. There may be many constraint for which it may not able to do it in 4 cycle, right. You probably you need say 7 cycle or 6 cycle and so on instead of 11 cycle. But that is something the variations of scheduling, but the basic intuition is just to identify the total latency and the start time of each operations, okay, within that latency limit. Okay. So, that is what is scheduling does. So, this is something is the overall scheduling problem. So, let me try to understand now what is the input, exactly input for the scheduler. Okay. So, the first input is the sequence graph. So, we have already discussed the data flow graph which represent the data dependency. Okay. So, for scheduling what we need the internal dependencies, right. So, the inputs. So, you can assume that these are the inputs, right. So, these are the all inputs, right, and these are also inputs, right. So, these are all inputs, not this one, this one. So, these are all inputs. So, when I am going to schedule, I am not bother about this what is exactly the value of the inputs. We only know that this is an input, and input is always available, you can assume, right, because at the start of the this basic block the inputs are available. So, what I can do, I can just simplify this sequence graph into sequence graph. Okay. So, this is the this data flow graph. I can simplify this data flow graph into sequence graph by just removing all these inputs and I putting a single node, right. So, what is called source node. Okay. So, source node is something is the node which represent all the inputs. So, I can just merge all these inputs into a single node and I will just make the sync node. Similarly, a program may have multiple outputs, right? There are multiple outputs. So, again I do not bother about what is the output and what is going on during the scheduling. So, what I can do, I can merge all these output node into a single node and that is called sync node. This is just to simplifying the graph, nothing else, right. This is still representing your inputs, right. So, this data flow graph representing your input program, and what I am just doing, I am just simplifying the graph, because during schedule my objective is to identify the start time of these nodes, not the inputs, right, and also the total latency. For that, what I can do is I can abstract out the exact inputs and outputs, and I can use a dummy node, source node and a sync node, so to represent the inputs and the outputs respectively. Okay. So, this is what I have done. So, this is just simplified the things, that is all, nothing else. Okay. And the way we have discussed that this is my start time, right. So, these are the actual operations, these are the actual operations. So, what I can do, I can assume that the source node is always scheduled in time 0, because my times always start from 1, 2, 3, 4, right, and this sync node will be always scheduled in the lambda plus 1, right, because that is not something is important for others. So, my actual schedule is 4 this, right. So, once I do this, I will assume that my lambda equal to 4 and the sync node will be always scheduled in lambda plus 1 time step, and this is always be scheduled, the source node will be always scheduled in the 0th time step. So, my actual schedule is from 1 to 4, right. So, that is the idea. So, once we try to take this program and try to schedule, I will always schedule this node at 0. So, it has no dependencies, and sync node is always be scheduled once the more my schedule is when my assigns of the time step of the actual operations are done, then I am going to schedule it in the last time step, because this is just the representative purpose, nothing for any complicated things. It is just for an abstraction of this data flow graph to a sequence graph for a better representation purpose, and deleting the unnecessary stuff which is not needed for my scheduling. Okay. So, my input behavior, which is a sequence of operations, will be represented by a sequence graph, that is my input 1. Okay. The next input is the operation delay, which I have not talked about yet. Okay. So, let me understand, or let me try to explain this operation delay. So, in hardware, once you try to execute an operation, it needs certain time, right, because it try to do these operations in the hardware. So, in that hardware it has a set of transistors and all, right. So, and now for each operations delay is not unique, right. So, for example, you always understand the multiplier is a big operation as compared to adder, right, because you can understand the multiplier is a lot of addition, right, lot of multiplication plus addition operations. So, obviously, an addition and a multiplier is not the same operation, and I hope you have already tried to implement a adder which is in some full adders and a multiplier, right, at the gate level, which is more complex operations. So, the delay to execute the multiplier will be much higher than the adder. This is just an example. So, you have say shift operations, plus, minus, division, modulus, any operation is possible. So, the delay of these operations are not the same. Now, the question is how do you execute a operations, the various operations in the hardware, what are the possibilities. Okay. So, you obviously understand that in hardware you have a clock, right. So, you have a clock, it is coming continuously. So, you know that this is one clock period, and whatever the operations get, this is another clock period. So, this is clock period 1, this is clock period 2 and so on. So, this is my clock period 3. So, whatever the operations are scheduled in the say in clock 1, that must be completed before the next clock comes, right. So, this is the clock period, right. So, this is the clock period. So, the delay of that multiplier must be within this limit, right. So, it should not go beyond this, then it is a so your result won't be stable, right. So, you can't get your correct results. So, now if assume that your addition operation is 10 nanosecond and multiplier is 30 nanosecond operation. So, to execute them in a single cycle, so suppose you schedule a minus operations and a multiplier operation in a time step, say time step 2. So, what, and since my multiplier is 30 nanoseconds, this clock period will be at least 30 nanosecond, right. It should be little bit more, say 35 nanosecond or so, because there are some setup time and hold time, but it should be at least 30 nanosecond, right, because otherwise this multiplier won't complete its execution within the given clock. Okay. And but the point here you try to understand that this is 30 nanosecond and this is 10 nanosecond, but my clock is 30 nanosecond. So, what is going to happen, this adder is remain idle for 20 nanoseconds, right. So, it just take 10 nanosecond to execute and then it just remain idle, because your clock is higher. So, it just wait for the next clock to come to do the next set of operations, right. So, that means if you, the possibility one is that you identify the operation which has the maximum delay and you set up your target clock like that. If that is the solution 1, that is your objective, then for faster operation it is a waste of clock, right. You could have done 3 addition operation here instead of 1 addition operation, right. So, your clock becomes slow, right. So, in this option your clock become very slow, and it is the clock period is determined by the delay of the maximum time taking operation, right, and your all operations are single cycle, right. So, single cycle means that multiplier will also complete in one cycle, adder, subtractor, shift, right shift, left shift, left shift, everything will complete their execution in single clock, right. So, this is one possibility, but we already understand that my clock will be very slow, and for the faster operator it will remain idle for many times. Okay. So, what is the alternative? The alternative is you make the slower things into multi-cycle operation. Okay. Multi-cycle operation. So, that means now I have decided to do this multiply in two cycle, right. So, that means the multiplier operation will take this many cycles, right, 2 cycles, and my clock period is double, right. I make my clock is 15 millisecond. So, my clock is fast now, right. My clock is faster now, and now because there is 2 clock, I can use the same adder to do 2 different operation within the time frame, right. So, this is where I just did this my multiplication operation, or the operation which is slower, I want to execute in multiple clock cycle. Okay. How to do that and the detailed architecture we can go into digital design, but let us assume that this is possible, right. So, to execute the things in 2 cycle, okay, this kind of design is possible, is available. So, what I can do aside that the delay of the multiplier is now 2, right. So, that means there is 2 cycle delay, it is not a single cycle delay. Earlier it was all operations are single cycle, but here operation become some operation which is slower, it is become 2 cycle operation, right. So, with this I can make my clock much faster, and I can execute the operation which is parallel to in parallel to a operation which is happening for multi-cycle, right. So, this is what is determine the operation delay. So, in practical circuit your delay of all operation may not be same, and delay is the number of clock cycle to execute the operation, right. So, for each operation now we have a delay associated. If the operation is single cycle like adder or subtractor, it is a 1, delay is 1, and if the operation is basically multi cycle, it will be 2 or 3. So, if it is 2 cycle, it is 2, if it is a 3 cycle, it will be 3 and so on, right. So, now for each node we have to determine, because in your based on your target architecture you might decide that I want to do my multiplication operation in 2 cycle or 3 cycle. So, you have to specify not only the sequence graph, but for each node in the graph you have to specify the delay of these nodes. Okay. So, that you have to specify. So, just to conclude complete this discussion, there are two other possible way you can execute this kind of mismatch of delay. So, this is the multi-cycling, the other operation is the operation chaining, right. So, what I am going to do, I will keep my clock 30 nanosecond slower clock, I am going to execute this multiplier for 1 cycle, but I am going to make these two things in chain, right. So, that means there will be one adder followed by a subtractor will be connected in a chain, and there is no register in between, right. So, the way these are all discussed, that there will be a set of register here, and this data will be, again there is a set of register here and there is a set of register here, right. So, it is basically after every cycle the data will be stored in some sequential element, but here there is no sequential element at this material, right. So, this if you are connected in a chain, right. So, this is not there. So, this is called operation chaining, that means still my clock is slow, but I am doing more operations in parallel. So, it will give you the same benefit like multi-cycle, but only the architecture will be different. So, it's you have to decide whether you go for multi-cycle or operation chaining, because operation chaining my clock will be slow, here clock is faster, and here architecture is simpler, because you do not have to make a chain of operator. It is basically I can utilize the same addition operation to do this both operation, but here I need 2 operator, right. So, it is the trade off between these two, but this is another possibility. By operation chaining also I can solve this problem of having 2 operations which have different kind of delay. The other option is the pipelining, which is very useful, that once you have this my operation is multi-cycle, I will still make the operation multi-cycle, say 3 cycle, but I do not wait to complete this operation and then I will start a new operation. What I can do, I can start the same multiplier for the different set of data, right. So, this is what is called pipelining, that means I am just adding some pipelining stages in between, which is basically set of registers, and then what I can do is I can just take a first set of data, say A and B, and I will just do the first part of the multiplier. So, I have to now develop my multiplier such that it is a 3 stage, right, and it will do some processing of AB and the intermediate result will be stored here, and in the next clock I am going to give A1 and B1, then what is going to happen? This part of the multiplier will execute on AB and this part of the multiplier will execute on A1 B1, and the next clock I am going to give A2 and B2, and so now the last part of the multiplier will execute on AB, middle part will execute on A1 B1 and the first part will execute on A2 B2. So, here although I make my multiplier multi-cycle, but I just making this kind of pipelining of the multiple tasks on the multiplier, right. So, I can this multiplier is equipped to execute on multiple data in parallel, and it will give you much faster performance. So, all this detail, so obviously the implementation of this pipeline will be different from this, and this multi-cycle will be different from this and so on, right. But these are all internal digital design things which is kind of abstraction to us in this course, right. So, suppose we have this kind of multiplier available in my database, and then I am going to do the scheduling, right. So, my objective is not to develop this circuit, because it is something is given, it is a library of resource is given to me, and high level synthesis is just given that schedule, when given this kind of resource, you just try to schedule the operations. Okay. So, these are the variations. So, the bottom line here is that you have the sequence graph, and also you have given the delay of the operations in terms of cycle. right. So, how many clock is needed to execute this operation is given, but the clock time is fixed, right. So, you mention that my clock is 10 nanosecond and so on. So, this is what is the given to us, right, and what schedule does? It determines the start time of the operation. Now, this start time will have to make sense, right, because if a operation which is a multi-cycle, you have a operation multi-cycle, you got to understand where it starts, right. So, if this is 1, 2 and 3, this operation starts at timestamp 1. So, T start of this operation will be 1, okay, start state, and it will end at timestamp 3. But if I know the start state and the delay of the operation, say the delay of the operation, suppose this is the node V I, right, and the delay of the node is D I, and then my T end will be T S plus D I, right, because it starts from 1. So, 1 plus 3, it is basically D I minus 1 basically, because so it start from 1, 2 and 3, right, and my D I equal to 3 in this case, right. So, schedule give you the start time where the operation starts, and if the operation is multi-cycle operation, I can understand what are the time step where this operation will be live or executing, right. And it is not that it is give this, but you have to make sure that the constraints are satisfied, right. So, so far the only one constraint we know, which is the data dependency. You identify the start time plus latency, but you make sure that so far the constant is only the data dependency. So, the data dependency constant is satisfied, okay. But your overall objective of the scheduling is just not the satisfying the scheduling, you might have different other goals, which is latency or area trade off, that I am going to discuss, okay. So, if as I mentioned that given the sequence graph and the delay of this node, your scheduling just assigning the time step, right. You just determine the operation that is going to execute in each clock, and the total latency is equal to 4, right. So, you can see here this is always 0 and this is always the sync node, which is lambda plus 1, okay. So, this is what scheduling does. So, if I just try to formally now place the scheduling problem, that you have a given a sequence graph where the each node represent a operation and this edge represent the data dependency, right. So, this is my operation and this is the data dependency, and you can assume that I have nodes say V0, V1 to Vn. So, this is my sync node always and this is my always source node, and these are the actual operations, right. And if there is a edge which is from say V I to V j, that means you have a data dependency from V I node to V j node, right. So, you have a dependency, that means you cannot execute these operations before that, okay. And in this particular discussion, operation chaining I am not discussing, but you can always extend the whole scheduling to operation chaining as well, okay. And what is the output? The output, okay, let me complete. So, this is the sequence graph, and you have also given the delay. So, that means the delay of each node D I for each node. So, V 0 to V n, and delay is basically is greater than equal to 1. You need at least 1 cycle to execute, right. So, either it is 1 or more, and also you might have given some constant on resource or timing, that I am going to discuss next. And your output of the schedule is the start time of each node. So, that means you identify the T I for each V I, right. So, you just for each node V I you just identify the T I where the operation is start is execution, and the overall latency, right, which is the number of cycle to execute the entire schedule. To interestingly, that can understand that start time is basically T n for V n and this is T 0. So, the latency will be this minus this, right. So, T n minus T 0, okay. So, this is how I can identify this, and obviously, this schedule should satisfy the dependency constant. This is what is called dependency constant, okay. That means, if there is an edge from say V j to V I, right. So, the way it is represented, if it is say V j and there is a V I, that means this is my V I and there is an edge here and it start at T j, right, and the delay is D. So, that means it will execute completion of the execution is basically T j plus D j minus 1, right. So, it will complete here. So, my V I can only start after this, right. So, this is what is given by this, that my T I, the start time of this node will be at least T j plus D j, right. So that is what it says, start time of this Ti must be greater than or equal to Tj plus Dj for all such edges, right, in my edge list. So it is not that you execute this, you give the timestamp, but the timestamp must satisfy the dependency constraint. Here, because the operation can be multi-cycle, so the constant is basically Ti is greater than or equal to Tj plus Dj, where there is an edge from j to Vj to Vi. Okay. So this is what is my scheduling problem. So based on your optimization goal, you might have different variation of the scheduling. There are three primary variations of the scheduling problem. The first one is the minimum latency unconstrained scheduling. Okay. So basically it is unconstrained, it just say unconstrained scheduling. So you can just remove this part, unconstrained minimum latency scheduling problem. That means you do not have any other constraint other than your data dependency. Data dependency is by default, you cannot ignore that, it is must there, right. So only thing, there is no other constraint. So that is why it is unconstrained, there is no resource constraint or latency constraint. You have just given the sequence graph and your objective is to execute everything in minimum number of timestamp, right. That is why this is unconstrained and minimum latency. The other variations is, now think about that, so doing this you might need lot of resources, right, but that much of resource may not available, right. So you might say that I have this much of resource, and you schedule the operations within that using the resource and you minimize the latency, right. So you try to schedule the whole behavior using a given set of resource, that means you have given a set of resource constraint, but your objective is to schedule the everything within minimum number of timestamp, right. So that variation is called minimum latency under resource constraint, right. This is another variation of the schedule which is called MLRC. Okay. The alternative variation is the just dual of this, that you have given a latency constant, that I have given a sequence graph and I want to execute this, it is a 10 clock cycle, and you identify the minimum number of resource needed to execute in 10 clock, right. That is what is the other problem. So you can have three variation of problem. The first one is that there is no constant, which is unconstrained problem, and your objective is to schedule everything in minimum number of timestamp. So that means you want to minimize your latency under no constraint, and the unconstrained is implied, there is a data dependency constraint is already there, because you cannot deny that. And for the other two variations where you have actually additional constraint, that you want to minimize the latency under a given set of resources, which is called MLRC, and the other alternative variation or the dual problem is that you are given a latency bound there and you want to minimize the resource to achieve that latency. That I have given say this much of latency, say I want to execute in say 10 cycle, and I want to identify the minimum number of resource needed to execute that sequence graph in 10 cycle with minimum number of resource. Okay. So these are the three variations of the problem, and we will see how to solve this problem, what are the algorithms of the problem in subsequent classes. So let us try to define this formally again. This unconstrained scheduling, your objective is to minimize the timestamp, the latency, you can assume this Tn, right. So the problem here is that the identifying the minimum value of this lambda or the latency is same as minimize the Tn, because so Tn is the start time of this node. If this is minimum, that means all things are done very early, my latent lambda is also minimum, right. So that means I can always say that minimize latency means you minimize the Tn or the minimize the start time of the sync node. Okay. So here the way you should define the given this V and the set of operation V and their corresponding delay and their data dependency E. So this is the input. You just identify a labeling of the operation phi, which assign so V to some integer number, which is basically the start time, right. So this is the assignment of the nodes Vi to some start time, some integer. So that was the start time of the node such that your dependency constant is satisfied, right. So what I am doing here is that my Ti, that is already discussed, that if there is an edge from Vj to Vi, then this will only start once this is completed, and that is given by this constraint, and this must satisfy for all E and your Tn is minimum, right. So that is will minimize the latency. So this is what is the definition of the unconstrained scheduling, which minimize the latency. Okay. The other two variations I will just quickly now define. The first one is the MLRC, right. So you have given a resource constraint. So how can I give up the resource constraint? first up we have to understand what are the resource available, right. So, the what kind of resource is available, the function you need, right. So, you have multiply, you have add, you have subtract, you have div and so on, right. So, what I can do, so usually in hardware adder and subtraction are same. So, I can just assume that these are ALU which can do this addition, subtraction, this kind of operations, and I have a mult, I might have a div and so on, right. So, these are the type of resource, and say there are n, these are the types are n RES. Okay. So, these are the number of type of resource available. So, for this example there are 3, right. One is multiplier type of resource, one is ALU type of resource, and one is a div type of resource. Okay. So, for each node I know what is the resource type, right. So, that is already given. So, for the node is the number of operations, and for each operation what are, which is the type of operation, is a multiplier type or whether there is a added ALU type or a div type is known to us, right. It is obvious from the program. And important is the resource bound. So, for each type of such resource some bound AK is given, right. So, A1 is the resource bound for the first resource type, A2 is the resource bound for the second resource type, and so on, right. So, suppose you have given 3 mult, 2 ALU, 1 div. So, that was the resource bound. That means, I have suppose if this is A1, this is A2 and this is A3, my bound is basically 3, 2 and 1. So, this is the resource bound A1, this is A2, this is A3. That means, it just specify how many multipliers is available in your target hardware, how many ALU available in your target hardware, how many divider is available in your hardware, right. So, that is the resource bound, and I have given the behavior now, right. So, your object is to identify the minimum latency under given this resource constraint, right. So, now this MLRC can be defined like this, given that schedule, this sequence graph and the delay that is already given, that you have the sequence graph and the delay of the operations. You try to and also given this resource bound, there are 3 inputs now instead of 2. You try to schedule the operation such that you minimize this Tn, you minimize the latency, and you satisfy both dependency constraint and resource constraint. So, earlier it is the same thing, it just unconstrained is basically just satisfy the dependency constraint, and now it is satisfying both dependency and resource constraint, because that is the things given to us. Okay. So, this is what this MLRC problem definition. The third variation is MRLC, which I have defined, that your latency given, you have given a lambda, you want to schedule everything in say 10 clock cycle is given, and you have given the sequence graph and delay everything. So, you have given this latency, you have given the sequence graph, you have given the delay of each node. What you want to do? You want to do a schedule which satisfy the dependency constraint and the latency constraint, and what is your objective? Your objective is basically minimize AK for k equal to 1 to n resource. So, I already know that this number of resource is 1 to n resource. For each k, I want to find out the minimum value of Ek, right. So, if you take the same example earlier, say I have given a sequence graph, earlier example what is given, I have given this 3 to 1 and I identify the latency is lambda, which is say 10. Now, I have given this lambda equal to 10, you need to identify the AK for each type, and which is basically say 3 to 1, right. So, you need 3 multiplier, 2 ALU and 1 divider, right. So, suppose this is what you want to identify. This is the dual problem, that you given this latency bound 10, you identify to schedule these operations within 10 cycle which satisfy both dependency and latency constraint, what are the minimum number of resource needed, right. So, that was the problem. So, these are the 3 variations of the problem, and this, I mean, we have different algorithm for all these variations, and we are going to discuss them in detail in the subsequent classes. In today's class, I am just going to discuss this unconstant, the first version, which you can understand is much simpler one, because there is no other constant. So, for that I am going to take 2 simplest algorithm, one is the ASAP algorithm and the other one was the ALAP algorithm. These are very simple algorithm. So, I am quickly cover this. Okay. So, the ASAP algorithm is basically as soon as possible. Okay. So, you have given the schedule graph, sequence graph, which is basically V and E, you try to schedule this behavior, and there is no other constant. You try to minimize the latency, right. So, that means the Tn, you try to find the minimum value of the Tn. So, how I am going to do it? I just schedule this V0 into T0, right, not 1, this is wrong. So, I just V0 is my source node, right. Now, for the rest of the node, what I can do? Since it is as soon as possible, so whenever a operation is ready to be scheduled, let us schedule it. So, how do I, what do we mean by the ready to be scheduled? That means its all predecessors are already scheduled. If its predecessor operation is not scheduled, I cannot schedule this operation now, because it will has to wait for that operation to be scheduled. An operation is ready to be scheduled, that means the operations which are basically all predecessors are already scheduled. So, you identify all such vertex whose predecessors are scheduled, we can assume this is a ready list. I just maintain this list, right, ready list R. And then just how can you schedule this? So, you know because schedule Vi, because these are the operations that can be scheduled now. So, you are now in timestamp, you are now try to schedule these nodes, and where I should schedule Vi, because if this is the node and there are these are the predecessors, right. So, these are the predecessors, this is my node Vi, right, and there is a it is depend on this, say this 3 this 3 Vj, right. So, this is say Vk, this is Vl and say Vx. When I can schedule only, so all these 3 must execute completed its execution. So, suppose this is executing, so this may be different cycle also, right. So, this might be a single cycle, this might be single cycle, this might be 2 cycle operation, right. So, I can only schedule once all these predecessors are done, once when the predecessors are done, the T. So, I can, so if this is my predecessor is say Vj, I know, and if it is taking Dj, then I only can schedule the operation at Tj plus Dj. So, what I am going to do now, because it might have multiple such predecessor, I am going to do the max of that value, right. For example, here if say this is 1 and 2, then since this is completing execution in 1 clock cycle 1, this will complete its execution in clock cycle 1, but this operation is taking 2 cycle. So, I can only start this Vi at timestamp 3, which is max of 1 and 2, right. So, this is the Tj plus Dj. I assume this is a single cycle, this is a single cycle, and this is a 2 cycle operation. Okay. So, this is how I can just do this. So, I will just identify this, and these are all scheduled, and once my sync node is scheduled, that means I am done, right. This is how I can execute these operations, right. Whenever the operation is ready to be scheduled, schedule it, but where to schedule based on the predecessor schedule, and whenever they complete, I only know the start time of this and their delay. From that I can identify what is the latest possible timestamp still what the predecessors are actually executing the behavior, and I am going to schedule it after that. Okay. So, let me just take the example here. So, so obviously, this is something there is a sync node, this should you can remove these things, right. And then, so in the initially you can see that these are all depends on the inputs, right. So, V1, V2. So, my ready list consists of V1, V2, V3 also, because it is also depend on this, right. So, V3, V4 and V10. So, what I can do, I can just schedule, because these are all inputs, I can schedule V1, V3, these all 5 operation into timestamp 1, right. Then these are all done. Then I am again going to calculate my ready list, and let us assume all this operation of single cycle. Okay. So, but if it is not single cycle, you have to identify the start time of the subsequent node. What is the now ready list? My ready list is now V5, then V6, then V9 and V11, right. So, in the timestamp 2 I can schedule these operations, right. So, this is my timestamp 2. Then these are all done, and I am assuming everything is single cycle, otherwise again schedule will be changed. So, then what is the ready list? I have only V7. So, in the timestamp 3 I am going to schedule V7, and in timestamp 4 I am going to schedule V8. So, I need 4 cycles. So, this ASFE tell us the minimum number of timestamp, because here you can understand that I am executing everything as early as possible, right. So, whatever this lambda I got from this equal to 4, I cannot execute this behavior less than 4 timestamp, because there is no constant here. I cannot have any schedule which can execute this behavior less than 4 cycle. So, ASAP give you this number, that the minimum latency needed to execute this behavior given behavior, right, because this is where there is no constant and I am executing everything as early as possible. So, that always ensure that it gives the minimum latency. Okay. And if it is a some operations are multi-cycle, I mean that is kind of your homework, you can actually try that, what will be the ASAP schedule for that. Okay. Now, I am going to explain ALAP algorithm. Okay. So, as the name suggests, it is as late as possible. So, my objective here is to schedule the operation as late as possible, right. So, if you remember that in ASAP what I did, I just start from the start node, right, or source node, because I want to schedule the operations as soon as possible, right. So, here intuitively you can understand, if I start from the start node, I do not know what is the latest possible state where I can schedule. So, the best idea to start from the sync node or the last node. Okay. So, how will start? So, I will start from the sync node. So, the Vn, and I schedule to the last the lambda. So, I have given this this pi, the number of schedule possible, the number of state in which I am going to schedule the operations. So, I have given that and just put into the last node. So, I just put the sync node here, right. So, lambda plus 1. Here one things to be noted here is that how do you guarantee that this the given lambda bar or the number of time step we need to schedule these operations is sufficient to schedule this, right. So, this we can check with ASAP, right. So, if the ASAP time is, so ASAP give you say lambda, and if lambda is greater than lambda bar. So, I mean I cannot schedule this operation in lambda bar. Okay, then I can have this check at the start and I will say ki no, it is not possible to schedule it here. Okay. But if my lambda bar, the given time here is less than greater than equal to lambda, which is my ASAP time, then it is schedulable, right. So, that check I have to do first, and then what is coming here. So, I will start with the sync node, I schedule it in lambda plus 1. Then how I will going to take a node say Vi, how do I know? So, first we have to check when this node can be scheduled is that when is all successors are scheduled, right. So, I have to just check all the node which whose all successors are scheduled, right. So, let us say I have decided a node such Vi, right. So, say suppose this is my Vi. Okay. So, this Vi I am to schedule now. So, when I can schedule it, I can only schedule it when all is successor such a way that in which time step. So, rather the way I should say ki I want to schedule it in Ti, right. So, what will be my Ti? Which state I can schedule it? So, the answer is that I should do such a way that if I schedule Vi at start his execution at Ti, it should finish, say suppose his executions say it is a 3 state cycle, right. So, this is my Di. Okay. So, my Ti will be such that if I schedule this Vi at start his execution from Ti, it should able to finish his execution before the start time of his successors, right. So, unless its execution is complete, the start node the successor node can start, but the successor node is already their scheduled is fixed, right. So, suppose for this node there are 3 successors, right. So, so these successors is 1 cycle, okay, and so there is another cycle is a 2 cycle, and there is another is 1 cycle. Okay. So, there are 3 successors of this node, it can happen, right. So, this node is nothing but is scheduled like this. So, it has 3 successor node, right. So, I have to determine the value of Ti, and how can I determine the value of Ti, that is what I try to understand. So, the objective here is that I have to make sure that if I schedule Vi at starting his execution with Ti, it should finish before the start of his successor nodes, and this Tj is already known, right. So, as I mentioned, this is the Tj of this node, start time is this state, for this is state, this is also state, right. So, what is I have to decide. So, these are the Tj for all successors, right. So, I am going to take the start time such a way that this Tj minus Di. So, Di is the execution time of this, right. So, if I take this node, say Di is say 3 cycle. So, basically let us try to understand that. So, this is 1, 2, 3, 4, 5 and this is 6. Okay. So, if I say this is 6, so 6 minus 3 is 3, right. So, then it could start from here, but if I start from here, it will overlap with this because this is starting from here, right. So, this is starting for 4 1. So, this is starting for 4. So, 4 minus 3 is 1. So, what I should take? I take the minimum of all the value of Tj minus Di. So, basically Di, it is not Dj, right. So, basically I have to see what is the start time of the all successor node, and from that I have to see who has the minimum value, and from that I will just subtract Di and that will be my Ti. Okay. So, that is how I should decide the start time of the node Vi, and this process will go for every iteration. I am going to select a Vi whose all successor is done, and then I am just decide his time by this logic, and I will keep doing it until my source node gets getting scheduled. Okay. So, if you take that example, the DFFQ example, this is my ASAP solution and this is my ALAP solution. Okay. You can understand this is where every time whenever there is operation is available, I am going to schedule it, and whenever in this case whenever I want to schedule it as late as possible, but I want to make sure that everything is done within 4 timestamp, right. Now, the question is what is this algorithm does, right, what is the use of this algorithm. So, first of all the first use of the ASAP, it gives you the minimum lambda, right. So, what is the latency bound? You can actually calculate the latency bound by ASAP, because you cannot have any solution which can give you the solution which is whatever the ASAP solution gives, you cannot have any solution which is lesser than that time. Okay. So, that something is very well understood, and this ALAP is something as late as possible, but this give a very nice property. So, let us consider this diagram, this operation, say operation 11. So, it is scheduled in timestamp 2, right. This is the earliest possible schedule, you cannot schedule it before that. And what is the timestamp where it is scheduled in the ALAP? It is scheduled in timestamp 4, right. So, this is my timestamp 1. So, what is this schedule? This is the ALAP, right. So, this is 2, this is 4, right. So, then this is the time which is the last possible time where it can schedule, it cannot schedule after that, because then this will not satisfy the lambda, and for this both case my lambda is 4. So, given a latency lambda, if I identify the earliest possible time where it can schedule by ASAP, and by ALAP I can identify what is the latest possible time where it can schedule. So, that something is the boundary, and what is the flexibility? So, it can be scheduled anywhere in between, and that is what is called mobility. Okay. What does it mean? So, by ALAP I determine what is the last possible time it can schedule, and by ASAP I identify what is the earliest possible time where it can schedule, and it means in between that ASAP and ALAP it can schedule anywhere. So, that gives the mobility, and this is very important in the context of the constant scheduling like resource constant or timing constant. So, when we have to schedule the operation on say on a given resource bound, you have to schedule the operation which is become critical or would become mobility become 0, right. It has to schedule. For example, you consider this operation V1 whose earliest timestamp is also 1, ALAP also 1. That means, this is a critical operation, it must be scheduled in timestamp. If you do not schedule it here, your total latency will not meet your target latency, right. So, this mobility determines the criticality of our operation. So, suppose you are in some timestamp, what are the operations that are available to be scheduled there, you identify the criticality operation which is the mobility, which is nothing but ALAP minus ASAP timestamp, and if the mobility is 0, that means it is now become critical for this timestamp, you must schedule that first, and then if the operation which has more mobility you can defer it. Okay. So, whenever you are going to discuss about the resource constant scheduling, this mobility is a very important factor which actually determine the if there are say less resource available and more operation to be scheduled, which operation to be selected for that time stamp. Okay. So, this is why this ASAP and ALAP algorithm is so important, although they never get used practically to implement certain design, but they are always run in background to help the other efficient algorithm to run, right. So, specifically this ASAP gives you the minimum latency bound, and this ALAP and ASAP combinedly give you the mobility of the operations, and from this mobility, which is the slack, this is the time where it can be scheduled. So, I can internally identify the slack of each operation, and based on my resource constraint or the latency constraint, I am going to schedule the operation which slack is less. Okay. So, for this example, you can actually identify the mobility of the operations, which is kind of a homework for you, and I have already identified the mobility of this operation is 2, basically this is 2 minus 4 is 2. So, operation with mobility is 2 is this node, so you can actually verify, and operation with mobility 1 is V 6 and V 7, and mobility 0 is this operation. Okay. So, with this I conclude today's class. I am going to continue this scheduling discussion in the subsequent classes. Thank you.